Yeah, so hello everyone. As Zora said, my name is Alex Cooper. I'm working at the University of Oxford. Um, and I'd like to thank the organizers of the conference for inviting me to talk about FRB emission physics and also for putting on such a great hybrid conference. It sounds like I missed out on the karaoke yesterday, but it's been a great experience online, so I'm very grateful. Before I start, I just want to highlight some of the great talks we've had already on emission physics. So we've had Navin, who gave a great overview about all different types of. Can you hear me, Lauren?
Yeah, yeah, it's all fine. I was just making, we can see your face now.
Great. Who gave a great talk on, I think, probably every different type of emission mechanism and the physics behind that and the predictions. And Kenzie, who gave a nice overview of the observational signatures and how perhaps they might be more naturally explained in many cases by a magnetospheric theory. So before I start, I want to take a bit of a step back and maybe for people that are slightly newer to the field, try and get at the question of why everyone talks about magnetars when we're discussing the progenitors of FRBs. And so we can look at the broad properties of fast radio bursts to try and understand this. Um, so the first and most obvious thing is that fast radio bursts are coherent, very luminous, and highly polarized in many cases emission. And what this points to, both from other types of sources that we observe in radio, but also on the theory side, is large and organized magnetic field structures to get at both the coherence and also the polarization properties. The second thing is kind of in the name, fast radio bursts. So we have these relatively short bursts of radio emission on the order of, say, milliseconds or shorter, and this points towards a compact emission region. And so we can roughly say that the lateral size of the emission region is constrained by causality. We have a factor of gamma here, which is the Lorentz factor of the emitting particles or the emitting region. And so if we take typical Lorentz factors mentioned in magnetospheric theory, so on the order of hundreds to thousands, we get something like the radius of a neutron star as approximately the emission region. And of course, if you have much higher Lorentz factors, you can have larger emission regions. So we think that we have magnetic fields, we have a relatively compact object. Does it have to be a magnetar or can it be a normal type of neutron star? And this is where the source energetics play a role. So what I'm showing here is the kind of corrected FRB luminosity, very typical values, and F here is a beaming fraction, and epsilon is some radio efficiency, how much of your energy goes into the radio burst. And what we can do is very roughly write down what the typical spin down luminosity of a neutron star with a given magnetic field and a given period will be, and we can see that there's orders of magnitude difference here. You can play around with these numbers, of course, but it seems like there's just not enough energy in the rotational reservoir to power these sources. And so we think that this is probably driven or powered by the magnetic energy reservoir. The final thing I'd like to point out, and this point was made by George in his talk on magnetar phenomena yesterday, is that we can look towards these galactic magnetars, particularly at high energy, their X-ray bursts, and make links to what we're seeing on the fast radio burst side. So what I'm showing here is two plots on the left for a repeating fast radio burst and on the right for X-ray burst from a galactic magnetar. And this is the wait time distribution. So if you've just seen a burst, what is the distribution of time you have to wait to see the next one? And both of these are characterized by these log normal distributions, in this case peaking around 100 seconds. In the fast radio burst case, we have higher time resolution. We heard in the last talk about how this lower bump which is also a log normal, may be some kind of subburst. In magnetars, we're not able to resolve this, but there's hints that there may be this lower wait time bump as well. So there's similarities here, and people have discussed similarities to things like earthquake distributions here on Earth, both in terms of the waiting time, but also things like the energy distribution. So that's a little introduction to fast radio bursts, why we think that magnetars might be their sources. And what we like to do, and we've seen this slide already this conference and beforehand as well, is classify our types of emission models into magnetospheric models on the left, where you have particle acceleration and radio emission from close to the neutron star surface within the light cylinder. And these non-magnetospheric models often invoking shocks and maser-like emission that occurs from relatively far out from the neutron star or some central engine. And we heard from Navin that some of the lines are being blurred between these two different types of models, shock models that might operate slightly closer to the neutron star surface. But I still think this is a useful way to uh, visualize these models in a simplistic manner. So we've heard a lot about some of the observational constraints. Given the talks that are going to come afterwards, I think it's useful to discuss a little bit about some of the multi-wavelength constraints that we have on some of these models. And particularly here, I'm going to focus on these maser shock models because they're very good in the fact that they have a definitive prediction that we can test with observations. So in the kind of basic version of this, and there's many different iterations of these models, you have some central engine. I'm going to assume it's a magnetar for now. And you have some outflow, which is usually ultra-relativistic and highly magnetized. And this outflow bears some resemblances to other types of transients, like gamma ray bursts, for example, but with two key differences. They're much lower in energy, and they're highly magnetized, and so you inhibit some of the non-thermal particle acceleration. But despite that, we still expect there to be these broadband multi-wavelength afterglows, and we can test for this. We can perform follow-up observations. Um, so I mentioned that this is slightly lower energy than something like a GRB, or a lot lower energy than a GRB. So the way that we can test this is with the brightest and most nearby fast radio bursts. And of course, as we've heard earlier in the conference, we had this kind of watershed moment in 2020 with this FRB-like burst from a galactic magnetar. And you can see some of the discovery plots here. Most exciting, I think, was this detection of an X-ray counterpart. So this occurred, as we heard from George, during this just after this extreme burst storm in X-rays. And the one burst that was associated with the FRB had peculiar properties, particularly in terms of the cutoff energy, which you can see on the right here, compared to all of the other bursts in that burst storm. And so within this maser shock framework, this model of FRB emission, this X-ray counterpart could be something like the prompt or early afterglow emission. And what that allows you to do is kind of tie your predictions for other wavelengths to to the data that we have for that X-ray counterpart. And so the first thing we did was in a paper in 2022 go after it in radio. Unfortunately, we were too late to be able to detect the predicted emission, as you can see on the right here across various frequencies. But there was a very fortunate optical upper limit presented in another paper by the Booch 3 telescope. And so the orange line in this plot is an upper limit, time dependent for the duration of the observation, and the red is this X-ray informed prediction from the maser shock model. And so it appears that the upper limit is about an order of magnitude below the predicted optical emission. And so I think this disfavors pretty strongly this nominal version of the maser shock model. So you don't need a galactic FRB to do this. You can do this for nearby or bright sources. And here I'm highlighting some of the work that's being done. So there's a few papers by Charlie Kilpatrick in the F4 collaboration, who's been able to rule out large parts of this parameter space for this maser shock model. Of course, you don't have this X-ray counterpart to tie the different parameters to, but you can still make a lot of progress in terms of trying to rule out parts of this parameter space. And there's a really nice paper by Aaron Perlman with these X-ray constraints, which for this very nearby FRB are starting to get down to the kinds of energies and luminosities that we observed from STR 1935. There's other ways you can do this, and one of the most interesting for me is actually performing radio observations of transients that are detected at other wavelengths. And so I'm just highlighting here some work by Alice Curtin and Yun Tian, performing radio observations either coincident to or slightly before or after short gamma ray bursts. So I think there's a number of papers predicting fast radio bursts from neutron star mergers. The rate just seems too low to explain all of the fast radio bursts, of course, but a fraction could still be powered by these mergers. And I think these kinds of works are really important. So moving towards the magnetospheric models, again, I'll refer you to Navin's talk on day one, which gave a nice overview of all of the different types of models, including many magnetospheric ones. what I want to talk about is focus on what do we actually mean when we say we've got a magnetospheric emission model, and where can we start to make progress here. So I think what we mean is that we have a set of events or a set of mechanisms that eventually will give rise to what we observe as an FRB. So we have some trigger mechanism. So for a magnetar emission model, this might be a quake or some kind of disruption to the surface of the neutron star. You have some mechanism for accelerating particles. You have to have some way of getting the observed emission out, radiate from these set of accelerated particles. And again, this is something we've been trying to understand for pulsars for 50 years. This is not an easy problem. And then we have to think about how does that FRB escape the magnetosphere? What parts of the observed FRB are intrinsic to the particle radiation, and what's imprinted as the wave escapes from the neutron star? So there's many different parts to this kind of complete theory of an emission mechanism, and I'm highlighting some of them here. I'm sure I'm missing out a lot as well, but the point I want to get across is there's multiple ways you can make a fast radio burst. So for example, you could say that maybe star quakes lead to these gaps that are not screened by pairs, which gives rise to the two-stream instability, and you get coherent curvature radiation. But I think it's important to remember that possibly many of these different mechanisms are viable, and possibly there's modularity between them. So you could have, for example, a slightly different way through this path to make a different type of fast radio burst. This said, not all sources should have the same chain, so you can have completely different chains of events if all of these mechanisms prove to be able to produce this kind of emission. I think we can go further and say that not all bursts from a single repeating fast radio burst should have this same chain of events. And also, possibly not all subbursts of a single FRB should have the same chain of events. So I'm highlighting here some of these high temporal resolution observations that have been done where we're seeing these micro shots or nano shots of emission in a broader burst envelope. And I think it's possible that perhaps you have a different type of trigger mechanism or a different region of particle acceleration or a different radiation mechanism that produces these micro shots compared to the rest of the fast radio burst. So we heard yesterday about some of the exciting new discoveries of these long period transients in many talks in the session. And I think it's useful to remember that this is only the third class of these luminous coherent radio sources likely powered by compact objects. So we have pulsars, and a lot of our understanding of fast radio burst emission physics comes from pulsars. But now we have this new class, and I think it's worth trying to understand what we can learn about this new class and how we can apply it to fast radio bursts. So we heard a lot about this yesterday. I'm highlighting here some of the kind of neutron starry properties that some of these LPTs have. So on the left, some of these spectropolarimetric properties of the GPM source, which look a lot like fast radio bursts and are very reminiscent of neutron stars. And on the right, some of these ASCAP sources where we have things like interpulses, mode switching, and of course this X-ray counterpart that Andy spoke about yesterday, which is very reminiscent of pulsations from a magnetar. So if we want to make this analogy, we need to be able to explain how magnetars can produce this emission. The first thing we need to do is understand how magnetars can be spun down to these very long periods, but retain their very strong magnetic field, because this radio luminosity often is in excess of the limits on the spin down luminosity. So they must be magnetically powered. So there's a lot of work going on trying to understand how we can spin these magnetars down, but retain this magnetic field. We heard yesterday about fallback disks, for example. There's other ways you can do this through mass-loaded winds, taking angular momentum away, possibly binary evolution channels as well. I think this is really useful in terms of understanding the evolution of these magnetars. But one of the key questions for me is I think, more directly related to the challenges of the fast radio burst emission mechanism, which is working out how can we get magnetically powered coherent radio emission from these sources. And so me and Zorawar wrote a paper last year trying to understand how this could be possible. And one of the ideas that we've come up with is essentially twisted magnetic fields that are driven by these active crusts. If you go above a certain critical twist, then what we show in the paper is that we expect particle acceleration, pair production, and this broadband radioluminosity to occur. And this is very similar in nature to the kinds of rotationally powered emission we see from pulsars, but here occurring on these twisted magnetic field loops in the closed field line region. The point I want to make is that the requirements for this kind of emission are relatively mild. So the twist that we seem to require to explain these LPTs is maybe 1 part in 10,000 compared to the background magnetic field. The crustal flow rate, this plastic flow as we call it, we think we need on the order of tens to hundreds of centimeters per year. But the luminosity scales very strongly with these parameters. And so you can imagine, for example, if you have slightly larger twists and of course much more sudden and violent crustal events, then you can get to those luminosities. You can bridge that gap to fast radio burst with relative ease. And I think there's a link in the physics as well. So as I mentioned, these are both possibly crustal phenomena. There's many models of fast radio bursts that invoke crustal slippages or star quakes, one of which I'm highlighting here on the left. And it seems like the parameter space for these two different types of models might be similar in some way. You need twisted magnetic fields, you need some active part of the crust. And another point I'd like to highlight is that longer periods in general will have a less dense magnetosphere and perhaps alleviate some of these problems with getting the fast radio burst out of the magnetosphere. The final point with respect to these long period transients, I just want to highlight one of these plots from Andy's paper where in the one epoch where X-ray emission and radio emission were observed in close proximity, the luminosity of the radio emission and the luminosity of the X-ray emission appear to be roughly the same. So perhaps the X-rays are slightly more luminous, but this implies that possibly radio emission from magnetars can be much more efficient than we thought. And I think it's useful to compare this to the radio X-ray luminosity ratio we observed from the galactic FRB from SGR 1935, which was much, much lower. So perhaps this implies that some magnetars can get to much higher efficiencies. Some final thoughts to end on. So I think we're entering this kind of era where we have a whole lot of data on fast radio bursts and not enough theories to explain it with specific predictions. And so to highlight this, I'm showing some of the observations of these hyperactive repeaters. So we have telescopes like FAST, which are observing hundreds of bursts per hour. And also this is kind of complemented by the hyperflash program that Omar spoke about a couple of days ago, where you have these high time cadence observations getting towards these much rarer but much more energetic bursts. And both of these works, which are on the same source, come to similar conclusions, which is that if you roughly calculate how much energy there is in the magnetosphere, making some assumptions, then these sources should run out of energy on kind of month to year timescales based on what we're observing from the FRBs. And so perhaps this means that we don't quite understand what kinds of magnetars can produce these hyperactive repeaters. Maybe we have a much higher radio efficiency, as I discussed earlier. Perhaps there's some replenishment of this magnetic field through, for example, expulsion of the core field, which can be much higher, or perhaps you have these significant twisted components. In terms of the next steps of making progress on fast radio burst theory and specifically on these magnetospheric models, I think there's a lot of use and value in developing these kind of models that you know are imperfect, but you can start to use to fit the data. So we know that, for example, we're going to miss out on some of these propagation effects that we don't understand. Possibly we're going to make many assumptions about what mechanisms are powering these FRBs. But I think if we want to make progress, if we have, in some cases, thousands of FRBs from these sources, we can begin with simple models and start to try and fit them to the data and get at these underlying parameters. And so I'm highlighting here a couple of works by Voisin and collaborators where they take these simple geometric models, which are essentially emission mechanism agnostic, and start to fit them to repeating fast radio burst sources. And this is not perfect. It's a very simple model, but you can start to get at some of these parameters. The final thing, I think that making this connection to galactic magnetars is crucial. And one of the challenges here is with the observations. So we have one example of a galactic FRB. We have what we think is a handful of examples of extragalactic magnetar giant flares now. But we have tens of thousands of fast radio bursts, and we have on the order of thousands of magnetar X-ray bursts from our own galaxy. And so making this connection is difficult, but I think it's a crucial step towards trying to understand what these sources of particularly repeating FRBs actually are. And this is part of the reason why I'm really excited by these new instruments that have large fields of view, despite being less sensitive, trying to increase this number of either galactic FRBs or local universe FRBs. And what I think this will help us do is actually leverage some of what we know on the theory side of how magnetars evolve, what their burst rate looks like as a function of time, and try and make the connection between, for example, young evolving magnetars and hyperactive repeating sources, or possibly older magnetars that produce maybe one or two bursts and look slightly different, both on the X-ray side in our galaxy, but also extragalactic fast radio burst sources. So I'll leave you with my summary slide, and I'm happy to take any questions now or on Slack. Thank you.
Okay. One question online.
Yeah, firstly, a question in the chat online. Hi, this is Pranav attending from Bonn. I'm curious whether any of the coherent emission models can be modified to account for the narrow emission bandwidths observed in FRBs.
Yeah, so I think there is a lot of predictions out there. There's a number of recent papers that claim, for example, that coherent curvature radiation can get these narrow bandwidths. I think many of the emission models that we have at the moment are focused on these kind of broad properties of FRBs, including the narrow bandwidths. So I think there are ways to get to the narrow bandwidths. Yeah, it's a question of trying to understand, I think, which parameters you need to get to the specific properties of one FRB, and then trying to actually fit those properties with these models.
Questions in the audience? Okay.
Hi, Alex. This is Naveen from Stanford. Thanks for the nice overview. I just would like to add a subtlety to one of your initial couple of slides on the optical counterparts from shock-based maser emissions. The prediction of a bright optical flash from maser emission is only valid in models that consider a paired plasma as the upstream medium where the shock occurs. If the upstream medium happens to be an electron ion plasma instead, then you would not expect a contemporaneous bright optical flash. That's it. Yeah. Thanks again.
Yeah, thanks. Yeah, I was specifically talking about this one kind of first model, but as I mentioned, there's different versions of this now. And for example, some of these occur closer to the neutron star surface and can get around some of these observational constraints.
Okay, we have a question online. Shami, can you unmute yourself?
Yeah, thanks. That was a great talk. I enjoyed it. Quick question, partly inspired by what Naveen just asked as well. What do you think about the non-detections at other wavelengths? How constraining are they beginning to be on some of these models? Like the non-detection in X-rays, non-detection in optical, how's that constraining some of these existing FRB models?
Yeah, so this is really difficult to do for extragalactic sources, even the nearby and very bright ones. The predictions are usually for fluxes lower than we're able to constrain. So I showed one plot with by Charlie Kilpatrick where you can rule out some of the parameter space for some of these models based on optical observations. I think it's difficult to do with the instrumentation we currently have, particularly in X-rays, right? We're just getting down to the X-ray radio fluence of SGR 1935 for this very, very nearby fast radio burst at 3.6 megaparsecs. So they are not super constraining, and hopefully this is why I'm hoping that there's going to be more of these either galactic or nearby local universe bursts that we just heard about, so we can try and perform these observations and get more more constraining upper limits or detection.
Yeah, there are
Okay,
questions. Please introduce yourself. Yep.
Thanks for the really interesting talk. I'm Pavan from Swinburne. I think you touched upon the radio reservoirs for some of these hyperactive repeaters and ways in which the energy can be replenished. Can you comment a bit more on kind of channels available, and what's your thought on sort of the models which can best explain such prolonged period of hyperactivity?
Yeah, so there was some discussion in the Slack about this as well, which I think is really interesting. I think so. At the moment, what we're doing is we're roughly calculating for a given magnetic field and a given efficiency and beaming fractions that we assume how fast these sources might run out of energy. But these are very simplified calculations, and so I think there's easy ways around this. If these are slightly more efficient radio emitters, then this gets rid of a lot of these constraints. But there's a lot more we think we know that magnetars, for example, are evolving. I think possibly Sam will talk about this in the next talk about how the core field might replenish the external magnetosphere. And also this isn't taking into account any twist that you might have in the magnetosphere, which adds energy to this external field. So I don't think that this is something to worry about in terms of a magnetar-centric model, but this is possibly suggesting that we don't have a complete picture of what kinds of magnetars can produce these hyperactive sources.
Okay, I think we need to go to the next talk. Sam, can you share your slides?
Yep, absolutely. Give me a second.
Oh, yeah. Let's thank Alex as well. So can we start, or I guess present?
Oh yes, sorry, it was a bit silent.
Yeah.
Give me just a second. Is that? Just trying to work out if I can maximize this without you losing the sharing. Can you still all see that fine?
Yes.
Okay, great. So thanks so much for the opportunity to give this talk. I'm really sorry I couldn't be in Montreal myself. In fact, I'm actually traveling, so I've been unfortunately dipping in and out of the conference. I'm actually going away from Montreal, technically. So this talk is it's kind of a step back in terms of what happens before we see an FRB. And this I'll try to argue is a bit of the problem we really need to understand, and it might help to disentangle some of these models that Alex was just talking about. So luckily Alex has motivated you all, because I don't really have time to do that. But broadly speaking, in astrophysics, if we see any bright source, any unusual source, and then it repeats somewhere down the line, the natural first assumption is to say, is it a magnetar? And it's a natural thing to ask, because this is an object where you've got a huge, not just a huge energy reservoir, but a huge free energy reservoir that you can potentially get out. And you have a valve, so you know the energy doesn't get out all at once because you've got this solid crust in the way. And the majority, I would say, of modeling, and this goes for, if you like, traditional high energy magnetar modeling as well as now FRB modeling, is to concentrate on the emission physics part of the problem. And it's logical because this really directly relates to what we actually see, what we observe. But clearly the pre-emission stage is crucial too. And emission physics modeling, generally the assumption is we know magnetars have got this energy and we just need to concentrate on the modeling of the particle processes and that kind of thing. And my argument is that you also need to look at the stage before that of, can you get the energy out where you want, when you want? And the reason to look at this stage is that this potentially allows you to constrain and possibly even disprove some magnetar-related ideas, initially in the context of high-energy short bursts all the way up to giant flares. But the same is true for if the central engine for FRBs and maybe some of these ultra-long period radio transients is again a magnetar, it's the same motivation, basically. So briefly in one slide, the activity of magnetars, again, high energy and radio activity, is likely gated by the star's solid crust. So what happens is you have a slow, unseen buildup of stress in the crust, and then a sudden release in some form, some of a burst. And in the recent years, more attention has been given to that pre-burst stage that you don't actually see. And there's some very challenging physics there, and it's very much a work in progress. Broadly speaking, some of the things that we think we know are that the magnetic field in the neutron star crust, for a sufficiently strong magnetic field and certain other caveats, evolves predominantly under Hall drift, which is a process that takes the magnetic field and essentially breaks it into smaller and smaller length scale pieces. And as you do that, you increase the crustal stress. So the crust is relaxed in the magnetar magnetic field's original state, and then the magnetic field starts to evolve, and that causes the buildup of stresses. We don't see the buildup of stresses because the crust, to start with, remains in that elastic phase until, just like if you pull an elastic band too hard, the stress becomes too high, you go beyond the yield stress of the crust, and then the crust in some sense has to break. The way which we think it does break is not a kind of brittle failure, but rather this plastic deformation or flow. And that plastic flow, it doesn't directly reduce the stress, it's more complex than that, but it seems to be, it broadly pushes you in a direction of reducing stress. And as it does that, because the corona of the magnetar has its foot points stuck in the crust, as you twist the crust around, sorry, as you have crustal motion, you twist up a coronal loop, and then you get to the emission part of the problem. So Hall drift in this magnetic field evolution problem, Hall drift is this first term here, so it depends on the curl of B cross B, and then the plastic flow piece, the evolution under plastic flow, is this advection term. So it's the curl of the plastic flow velocity cross product with the magnetic field. There's one big problem, I would say the biggest problem here in crustal failure physics is that we don't know how far any given failure extends. And this is really hard to work out. The simulations we have are really truly microscopic simulations. So it's molecular dynamic simulations, and you can't extend that to the whole crust. It's easy to see why if you think you can imagine you have some very tiny region of the crust which has gone beyond the yield stress. You don't expect the entire crust to just start plastically deforming if the rest of it is below the yield stress. And although there are analogies with the terrestrial context and even some kind of statistical similarities, we don't have the luxury of having tectonic plates like in a magnetar like we do on the Earth. So we don't know where a given failure would normally stop. So one way to kind of imagine, to kind of get past this conceptual problem is we can look at what the kind of stress that Hall drift produces, and this is characteristically roughly 1 kilometer squared patches that develop. So those should be you can imagine semi-independent cells where the crust evolves, and then because some activity is a lot brighter than others, you get all the way from the lowest energy events like short bursts or some FRBs up to giant flares. There should be some mechanism for those cells to communicate with each other. And each cell should have a long phase unseen when it's in its elastic phase where the Hall drift is increasing its stress, followed by a quick plastic drop in stress. So if you imagine dividing up the crust in this way, so flattered to see this figure a few times before my own talk. If you're in the Hall phase, you have these loops on the left, these magnetospheric loops where the crust is static, so this coronal loop is untwisted. On the other hand, if you then enter the plastic phase, to have a plastic flow that doesn't extend beyond that cell, you have to have a kind of a circulation in the theta phi direction, and that causes a twisting of that local coronal loop. So that on its own will give you small bursts. If you then want to explain everything all the way up to giant flares, I know we don't care about high energy here, but that's part of the motivation for the, part of the motivation for this is both seeing how you can get radio and X-ray emission. So if you have this kind of communication between cells, you can get a stress evolution that looks like this on the left. So I'm not sure how many of those frames are displaying for you, but the point is that when you get a communication between groups of cells, you can get a giant flare, and then you lose a lot of stress in that region, and you're left with more isolated patches of stress afterwards. And broadly speaking, what happens then is you see some very violent activity early on, and then you see smaller bursts and periods of quiescence. The interesting thing about this picture is that it's different from this traditional sketch of a magnetar corona where the entire corona is twisted up. If that really is what a magnetar looks like, you wouldn't expect to see any radioactivity at all because it's basically screened out by this charge dense corona. On the other hand, this model that's built up from ideas about crustal failure and Hall drift points to a corona which isn't that large scale self-similar one, but rather is a complex one where you have local regions which are low twist, which might be associated with FRB emission, but the same source, as indeed we saw in like SGR 1935, can have some also highly twisted coronal loops, which you would associate them with X-ray emission. The point here, though, is that if this is all part of the same picture, you should expect some statistical similarities there as well. Okay, so then just moving, kind of jumping from FRBs to these ultra-long period sources then, and the connection isn't obvious at first, and this in fact was a bit serendipitous. I was looking at what happens very early on in the life of a neutron star when it starts to become superconducting. So this happens just a few minutes after birth. And if you've seen these experiments on Earth, what a superconductor tries to do below a certain field strength is to expel a magnetic field that runs through the superconductor. The problem is with a neutron star, you can't expel the field. The field is intrinsic to the star. And instead, the two sort of traditional limiting pictures for what might happen are either you manage to expel the field somehow, so that would be the picture on the left. So you have a crustal field which has no connection with any core field. So this purple region is zero field. Or you have a magnetic field that threads the entire core. And the connection here with magnetar activity is that all magnetar modeling, so the evolution of this Hall drift equation, assumes that you have to have an expelled field. If you don't have that, it turns out that the simulations just don't display any magnetar activity at all. What's interesting, though, is if you consider this process of how that expulsion might occur, and there's a tension between whether it can or different factors that dictate whether it can or can occur fully, you also get these intermediate states where you can have the field expelled from, so like the second or the third plot here, where it can be expelled from most of the core, most of this kind of, purple ring, but then thread the purple ring in some select places around the equator or the pole or various more complex geometries. And so having looked at this, I then discussed with some colleagues about let's look at what happens if we evolve the magnetic field in these new cases. And there was a big surprise, which turns out, well, I'll show you the pictures, the videos actually. So this is a canonical traditional magnetar simulation. So the field is expelled from the core. It's developing in the crust. You're looking at these black lines are poloidal field lines, and the color scale is the toroidal field. You see a peak of activity around 10, 20, 30 kiloyears. It's around now. And then as you wait longer, the star becomes less and less active. So you expect it to become less and less active into old age, which is fine for a typical magnetar where we do expect that the activity reduces as you get towards, let's say, 100 kiloyears. On the other hand, we now have reasons to hope, let's say, that there could be such a thing as an old magnetar which reactivates at far later times. And just see if I can play that again. So if we look at then the right-hand plot, so this is one where you've got this equatorial hole. You have the same kind of initial evolution from the outside inwards, but you also, from the cross-core boundary outwards, you get a different kind of, you get an extra piece of evolution. Those two kind of packets of toroidal field meet in the middle, and there's an interplay that means that actually the activity in this model starts to become really enhanced about the point it's dying off in the traditional model. And the star is actually seems to be becoming more and more active around the 1/10 of a megayear, probably beyond that, but for numerical reasons we haven't been able to pursue it further. But the point is that this would really be an old magnetar, and it comes about naturally just from considering that early time expulsion process. So the broad message here, sorry, no, it's a bit rushed when you try and get two different topics into a 10-minute talk, is that if you look at take a close look at the physics that actually gets the energy out of the star, so the Meissner effect and the process of crustal failure, it stops being just a hope that you can explain everything as a magnetar, but it actually becomes natural to expect magnetars to be FRB emitters, or in some cases to become these ultra long period sources. And that doesn't contradict the fact they can also be typical X-ray bursters as well. So thanks for your attention, and I'm very happy to take any questions. If you want to email me afterwards, that's my address. I'm afraid I'm not on the Slack very much because, yeah, I'm rushing around at the moment.
All right. Any questions? Okay. Please introduce yourself.
Hi, we are from University of CES. So we always treat the star-quick wave as monochromatic waves. So is that a good assumption or a good approximation?
You always treat the what? Sorry, the.
In other words, I mean the spectrum of the star-quick waves as something like a third function here, as just a monochromatic wave. Monochromatic wave. So is that a good approximation?
I don't know that I could say it's a bad approximation necessarily. It's
Maybe we should consider some nonlinear process here. I don't know.
I think it's the actual process of the crustal failure and then the waves you set off from that's sort of I don't think what I'm doing here would greatly constrain that, because it's a sort of a separate bit of the dynamical problem. So really what I've been doing here is a kind of it's looking at the long time evolution of magnetars and how at different phases really you have different kind of stress patterns, and you can associate that with different levels of activity. But I think what you're talking about here is really what the dynamics of this process are. So as far as I know, it's a good assumption. I don't have a problem with it anyway. I don't know enough to have a problem with it.
Okay, thank you.
Thanks.
Any other questions?
Hi, I'm Adam Landman from MIT. I was wondering if you had any thoughts on how if there were a companion star that might interact with the neutron star crust and induce any of these kinds of failures that you're describing.
So if you have a companion star of a sort of similar size to the neutron star, you mean, or?
Yeah, or like a tidal interaction of some kind.
Right, yeah. So if you've got tidal interactions, you've got a different source of stress. I think this source of stress that I've got here is is universal if you have a strong magnetic field. That stress though should interact with the tidal deformation as well, in a way that I wouldn't be able to tell you off the top of my head. And also, obviously, if you've got the companion, it might be that you might eclipse some activity that you might otherwise see. Like you might just, if you have a situation where you have any kind of, I guess, for example, accretion or whatever, I think broadly speaking, you would always tend to reduce your chances of seeing any radio emission from that system, probably, compared with the isolated star, just because the environment is messier and it's easier to kind of screen out the accelerating electric field that you would need for radio emission. Beyond that, yeah, I'm not sure. The tidal field would definitely cause an extra source of stress beyond the magnetic stress, and there would be some interaction there for sure.
All right, thank you.
Any other questions? Okay, let's thank the speaker again.
Thanks very much.
Our next talk is a pre-recorded talk from New Zealand, which is, I think, 2 a.m. there.
Hi, my name is Clarinda, and I'm currently a master's student at the University of Canterbury in New Zealand. This is work I've done as part of a summer project at Swinburne University in Melbourne, Australia, which was focused on the effects of beaming in fast radio bursts. So the main aim of this project was to look at the directional dependence of the emission, which is what we call the beaming. By trying to reproduce observed energies of known FRBs, we can analyze how beaming may influence their energy distribution. And this theoretical explanation can help us to understand the role of beaming in observed energy distributions, potentially helping us to further constrain the emission mechanisms or progenitors of FRBs. Modeling the energy distribution of FRBs is typically reliant on the number of bursts. So FRBs with fewer bursts are reliant on the cumulative distribution function to be modeled by. So in the case of 121102, where there were fewer bursts, it was modeled with a power law that ranged from the power law index of -1.1 to 0.2, and FRBs with more bursts can be modeled by their probability distribution functions. So the burst energies of FRBs are typically between 10 to the 36 and 10 to the 41 ergs. However, the limits on the lower end of the observed energies is caused by telescope sensitivity. Activity windows with more bursts are also more detailed than those with fewer. So with both of these basic factors in mind, we can make the assumption that we are only observing the most energetic FRBs, and those with many bursts are easier to approximate an energy distribution for. In particular, Li et al. Did an analysis of 1,600 bursts from FRB 121102 over the span of 47 days. They found a bimodality that appeared and then disappeared over a period of days. And they were able to model this energy distribution with a combination of a generalized Cauchy function and a log normal function. And they suggest that this may mean that possibly more than one emission site or beam shape would be required to result in this type of energy distribution. Similarly, Zhang et al. Also did a study on 800 bursts from another FRB, 2011-24A, where they analyzed 800 bursts over the span of 4 days. And they were able to model their bimodal energy distribution with an exponentially connected broken power law. Both of these analyses are using more complicated functions to try and recreate these observed energy distributions. However, they're not considering the beaming. We are going to try and recreate the same observed energy functions, but with beaming and hopefully simpler functions. As we consider beaming to be the effects on the observer's position relative to the center of the beam on the observed energy distribution, we need to consider three main features: the angle of the observer relative to the beam, the shape of the emitted beam, and its underlying energy distribution. Firstly, we assume that we can observe the beam from a random position and angle. So for this, we simulate a bunch of random X and Y angles, which describe the angle of the observer relative to the FRB center of the beam at the origin. And so that we then exclude angles that are outside a R max, which is past that point, an observer would not be able to see a emission from the FRB. So going back to the diagram from before, this shows how we can think about a beam from an FRB source. If an observer is angled in line with the FRB emission, i.e. at R0 or between RP and minus RP, then they will observe the maximum energy. If the observer is positioned further away between RP and Rmax, then they will still observe the FRB, but likely at a lower energy. However, if an observer is located at an angle that is greater than Rmax, then they will not be able to observe the FRB emission. So based on the current literature in FRB beaming, we chose two main beam shapes, a Gaussian beam and a relativistic beam. And so on these graphs here, I just have the strength of the beam versus the angle out from the center. So it goes from 0 to 1, and so at 0, the Gaussian and the relativistic beam are also at their peaks. So at that angle away from the center of 0, then you would see the maximum energy. So we also consider the case of a single energy, and we can plot these simple energy distributions and their corresponding equations. So for the Gaussian beam, we are able to choose the width, and for the relativistic beam, we can choose a Doppler factor. We also have to simulate a secondary angle, which is theta, which is drawn uniformly between -1 and 1. We are also able to combine the isotropic beam with the Gaussian and the relativistic beam in a piecewise function to create a central core or a plateau out to a certain angle RP. This gives us a plateau region in the observed history diagram, and at an angle greater than RP and less than Rmax, the beam shape is given by either the relativistic or the Gaussian equation. From looking at these distributions, we can see that the Gaussian beam seems to just be giving us a uniform distribution. However, the relativistic beam results in an energy distribution that looks somewhat like a power law. So we are also able to consider different intrinsic energy distributions: a single energy, a power law, a broken power law, and a log normal intrinsic energy distribution. The single energy is unphysical, but we use it as a reference to see the effects of the beam shape. Initially, we did consider the broken power law. However, it had a similar effect to the single power law, and it didn't create any features that would favor a bimodal energy distribution. We also found that throughout beaming, the effect of the broken power law was not conserved. Regardless of whatever beam we applied, we would end up getting just a single power law out of the intrinsic broken power law distribution. For this reason, the simulation results that included the broken power law are excluded from the rest of this talk, as they didn't provide any significant difference to that of the single power law. So the graphs I have here are just the intrinsic energy distributions if there was simply isotropic or single energy emission. Below the graphs, I've also included our definitions for the power law and log normal distributions. For the power law, we are able to change alpha, the power law index, and with our definition of the power law, alpha must be less than -1, so that as E tends to infinity, the probability of a burst tends to 0. For the log normal distribution, we are able to change S, which is the location parameter. Taking all of these steps into consideration gives us our simulated results. Just to run through it again quickly, we first generate a number of observer angles, we then create a beam shape, and then we apply an intrinsic energy distribution. We then get an output of an observed energy distribution. So we can look at the different combinations of intrinsic energy distribution with beam shape. So for this graph, we have the rows being the intrinsic energy distributions, and the columns are the different beam shapes. Any fall off at the low energy end is due to telescope sensitivity, or equivalently, the maximum angle at which the FRB can be observed from. Taking a closer look at these energy distributions can help us understand them better. So firstly, looking at the Gaussian beam shape with an intrinsic power law distribution, we see that the Gaussian just gives it a uniform top, and then there's a power law drop off. And this doesn't give us anything close to a bimodal energy distribution. So then we take the case of a Gaussian with a central plateau region. So we then get a uniform distribution with a singular high energy peak. And so this isn't quite yet a bimodal energy distribution, but we can see that having a central plateau helps to give us this high energy peak. And it also means that if any observed energy distribution that needs to have a second peak must have a beam shape that falls off slower than a Gaussian. So finally, we combine a central isotropic core with a log normal intrinsic energy distribution, a central plateau with a relativistic beam drop off with a log normal intrinsic energy distribution. We get two distinct peaks. And so therefore, this combination allows us to have a bimodal energy distribution. So now that we're able to create a bimodal energy distribution, we wanted to see if there was any sort of relation between the size of the plateau and the shape of the energy distribution. It turns out there was a relationship between the log of the ratio of the height of the high energy peak to the height of the valley in between the two peaks. and the angular size of the plateau region or the central core. So by I, we define the bounds of the bimodal region between 0.3 and 0.83 for RP. And so after simulating a range of observed energy distributions with varying plateau sizes, we can define a linear relationship in the bimodal regime. So that is the log 10 of the ratio is equal to 1.79 times RP minus 0.53. So we can take our two bimodal FRBs, 2011-24A and 1211-02 that we saw earlier. We can plot their energy distributions, and we can then determine the ratio of the peaks to determine the angular size of their theoretical central core. For 2011-24A, we get a high energy peak just below 60 and a value just below 50. And then we can do the same thing for 1211-02, and we can plot these onto our graph. So we find that for 2011-24A has a peak to valley ratio of 1.54 and an estimated theoretical central core size of 0.4. And for 1211-02, it has a peak valley ratio of 1.84 and an estimated plateau region of 0.54. And this, of course, is dependent on the bin size that we've done and also the time window that we analyze them in. And so one thing that we've started doing is to look at the time evolution of the ratio. So this is a graph where you can see the time evolution of the ratio of FRB 1211-02. So it starts off with its RP in the bimodal regime. It drops back down to the unimodal regime, and then it jumps back up again and stays in the bimodal regime for a while. So while this graph doesn't consider errors, it does show that the FRB tends to stay in like its particular window, and it doesn't just tend to jump sporadically. So that gives us something to think about. So to summarize, we find that we can create in
Okay. We could start. Pavan, Uttarkar, you'll talk about extreme scattering in the FRBs.
Thank you.
Okay.
Right. Hello, everyone. I'm Pavan, a fourth-year PhD candidate at Swinburne University of Technology. Today, continuing with the spirit of this particular meeting, I'll be talking about one more repeater, FRB 2024-0114A. Oh. Yeah. Is it better now? Yeah. Absolutely. FRB 2024-0114A does not require any introduction. We have seen many talks about it over the last couple of days. However, I'm here to give you a unique perspective of this source using the UWL on Montréal Radio Telescope. Now, this is a very unique instrument in the whole wide world. Yesterday, we heard a talk about the follow-up of the source from ATA, wideband follow-up. However, I'm here to take that a notch higher, use 6:1 bandwidth or 2.6 octaves of bandwidth between 704 to 4032 megahertz, and then show you some unique characteristics of the source. The plot here on the right shows this beautiful emission across the whole band. If you look at the y-axis, it's 704 to 4 gigs for a Magnetar J1810. Now, because of this high fractional bandwidth, it makes it an ideal instrument for repeater follow-up, especially considering its reliable wideband spectropolarimetric information that it can give us. Now, coming to the source itself, this was reported by Zhang back in January 2024, and a lot of us started following up the source. Now, to that effect, we have detected over 5,500 bursts from the source until 1st of June. And the reason 1st of June was because parks went under maintenance after that. And this is, mind you, with the entire information of about 3.3 gigs using the UWL. This gives us an unprecedented wideband insights into the spectropolarimetric and temporal behavior of the source. One of the brightest bursts that we have detected to date is about 2,500 sigma. The plot here on the right shows that, and this shows this beautiful SATCOM1 structure as well as multi-peak emission. I did this in November meeting as well. Back then, the cost per FRB was about 28 Australian dollar per FRB. Now it's 30 Australian dollar. It seems to have hit an inflationary patch, but I can assure you that this is just transitionary. Now, when we sort of zoom out and look at the whole follow-up of 16 months of the source, and see how the burst activity has been evolving, this is what we exactly get. Now, let's walk through this slowly. The top panel, panel A, shows the burst activity over 16 months. The purple color shaded region shows the number of UWL hours that we have spent looking at this particular source. Eagle-eyed among you would have already noticed that there have been multiple burst storms from UWL that we have observed. And the panel in between, panel B, shows the spectral extent in the error bars, and the black color points show individual center frequencies of bursts, and the red color point shows the center frequency, average center frequency of all the bursts per epoch. Now, as we can see here in the bottom, if we only had a narrow band instrument, we would not have been able to catch many of these burst storms. The bottom panel shows the RM. RM had stayed fairly consistent over multiple months. However, starting about 6600 MJD, we started seeing a precipitous decrease in the RM of about 0.9 RM units per day. Now, when we started the initial follow-up, we did not have a continuous coverage or uniform coverage of the source. That's why you see a lot of gaps here. However, starting October last year, we started getting more and more uniform coverage. And that is why we will focus on two of these burst storms here. Now, one of the very interesting things about the source is that whenever it goes into burst storm mode, it slowly ramps up and then it again ramps down slowly. However, in these two burst storms, we can see here that it ramped up, and then as soon as it had to reach its peak activity, the burst activity suddenly quenched. It ramped back up and then came down gradually, and that is what we see in another burst storm as well. Quite interestingly, this was also associated with a shift in the center frequency. For example, just after this burst quenching, which is shown here in the green color shaded region, in the middle panel, it shows this sudden quenching or sudden shift in the center frequency of emission. Now, in our quest to sort of understand what exactly is going on, we turn to one of the potential models, which is the extreme scattering event. Extreme scattering events are nothing new. They were first reported by Fleidler et al. Back in '87, and a Gaussian lens interpretation was given by Clegg et al. In '98. And this was sort of extended to FRBs by Cordes et al. In 2017. Now, the plot here on the right shows this sort of Gaussian lens interpretation. Because of plasma underdensities and overdensities, the focusing and defocusing regions would essentially cause caustics, because of which there would be apparent increase in brightness of this particular or of a source. Now, this has been observed in quasars, and this has also been observed in pulsars. For example, Kerr et al. 2018 showed this ESC effect in young pulsar. If you sort of concentrate on the bottom panel, this is a narrowband instrument, and we can see this apparent brightening and debrightening of this particular source. Now, let's flip the switch here, and instead of pulsar, let's see how we would see an FRB in that context. Now, again, let's walk through this plot slowly. The top panel shows the MJD of individual epoch of follow-up. The dynamic spectrum is essentially taking all the bursts, about 20 sigma, in particular epoch, averaging across time, stacking them right next to each other. The white color stripes essentially show you the transition between one epoch to next epoch. In the initial days of follow-up, as we saw in our previous plot, we did not see any emission about 2 gigahertz. As we went along, we saw more and more emission across the whole band. It again sort of drifted back, went up, and then started emitting in the entire band, and went down and again did this chromatic kind of behavior. Now, this is not to be confused with chromatic activity of 1809-16B. This is way more complex than that. Now, one of the other things to notice out here is the fact that this has some sort of a spectral memory. Over weeks and days and weeks of time scale, we see this sort of lingering around of center frequency in similar bands over multiple days and weeks. Now, when it's not just the spectral memory over multiple days and weeks. We have been looking at spectral memory over multiple minutes, millisecond to minutes time scale. This has been sort of seen in 1202A observations using narrowband instruments. However, here is an example of fairly narrowband burst, for that matter. This is the whole band of UWL from 0.7 to 4 gigs, and the small burst, which was fairly bright, that we detected. Now, this also shows this preferred band of emission with same center frequency and same burst bandwidth. If I run through different bursts in the same epoch, we see these different bursts which have exact same center frequency, exact same burst bandwidth, which are separated about 10 minutes. This is sort of consistent with the amplification of specific bands through ESE. For example, if we just use the Gaussian lens interpretation and use 10 tens to 100 scale AU lens, this is what we kind of get in terms of gain parameter or sort of the gain function, or the band of UWL from 0.7 to 4 gigs. And the x-axis here is transverse scale, which is a proxy for time because we do not know the transverse velocity of the source exactly. And what we would see is if we take a slice across x-axis, we would see that there would be amplification over multiple of the same band over multiple time scales. Now, most repeaters have sort of been speculated or sort of known to live in a more complex magnetoionic environment. Therefore, plasma underdensities and overdensities, information of this is nothing surprising. Now, we can explain both of these using different length scales. For example, the long time variation or sudden burst quenching, as well as the spectral preferred spectral band of emission in a single E. Now, if we take that slice and then like stack all of these bursts that we detected, I've shown 3 of these bright bursts here, and sort of plot the gain function across the whole band, we would see that there is this specific discrete bands where it gets amplified, and which is kind of consistent with what we are looking at in terms of observables. Now, it's not just that. If this also sort of points, because we get very bright bursts of the order of hundreds of sigma. And as we saw in Manisha's talk today morning, high redshift FRBs are really exciting. And if we take this burst, which was about 500 sigma, and sort of redshifted, and just 3.5 megahertz at Montréal would be easily detectable by Chime at a redshift of 6. Again, indicating an exciting possibility of detecting such sources in high redshift universe. Now, sort of summarizing and coming to the end of this talk, we have detected over 5,500 bursts by Montréal. This huge number of bursts with such large spectral bandwidth gives us a fairly unique view of the source. Combination of ESC and intrinsic effects are likely at play in some of the emission that we see from the source, and the macro spectral behavior in terms of spectral memory can be explained by multiple length scales due to complex magnetoionic environment. This also kind of opens up an exciting possibility of FRBs and high redshift universe. Thank you.
Nice to talk to you. Have questions? Okay.
Hey, Pavan. It's Molson from here at McGill. And so I think there are probably a few people in the audience champing at the bit to ask the same question. So you had this big dynamic spectrum that's stacked up from all the different bursts over a wider time period. Have you done anything like just taking the power spectrum of that data to look for things like scintillation scales like they do with pulsars?
Yes. That's ongoing work, which is being sort of headed by one more PhD student. And we have been looking at scintillation and sort of analyzing what we can derive out of it. But yes, that is surely a thing that is.
And so I guess just as a very short follow-up, what's the spectral resolution for the UWL?
It's 0.5. We use 0.5 megahertz with 64 microsieverns. We can go down, but yes, that's okay, just great. Data constants.
Thanks so much.
Very interesting results, Pavan. So quick clarification question on the property of the bursts during the peak of your outburst cycle. Do you just see a switch in the central frequency, or do you also see a switch in the luminosity of the typical luminosity of the burst that arrive?
Yes. So there is apparent sort of brightening of that whenever we see the sudden or not sudden, like after this quenching.
Yeah.
In the lower band, we see more and more bursts which are higher SNR. Although it varies from burst cycle to cycle, so it's not strictly correlated, but yes, there is indication of that.
Very interesting. Thank you.
Can you pass it along to Duncan?
Pavan, this is Duncan Lorimer from WVU. Very nice talk. Could you show your sort of giant waterfall plot again? That one.
Yep.
So is it true that you almost always see it at the highest part of the band? It looks.
Oh yeah, so that's a good question. I was anticipating it. So because of the fact that we don't the calibration model that we have for flux calibration at Parkes is not very well behaved at higher frequencies. There are some of these, for example, these epochs where there are no bursts, but here there are truly bursts. These are just the baseline issues.
Okay.
Yeah.
Right.
Yeah.
Ziggy Pleunis at the University of Amsterdam. Beautiful data. I have a question about your extreme scattering event interpretation. If you look at the rate of its ECEs are happening for quasars, for example, does it match up, or is it surprising that we find it in one FRB out of our sample?
Yeah, that's a good question. In terms of quasars, the ESCs are essentially because of, some of the Bannister et al. Essentially sort of constrain the plasma distance, lens distance, sorry. So that was more of a galactic scale. However, in terms of rates, we see for this, but again, we don't have a wide band information for a lot of repeaters. So I think it's more common than we anticipate, but yes, it requires wideband information in order to properly say that for sure. Yeah.
So you mean you are a little bit surprised that you find it in one FRB out of the sample?
In one of the bursts or for this particular source?
Just one sideline to one source out of all of the known repeating sources.
Yes. So I'm not that surprised, so to say. I would expect that because they live in more complex ionic environment, this should be more common. But again, there are 5 or 6 FRBs which have been followed up. So there is a combination of things. One, we need a highly active repeater. The second one is we need a wideband information in order to say that for sure. Here we had both of them. So it's possibly a more instrumental sort of observational bias rather than something related to the population itself.
Andrea Possenti from INA. Is there any trend between the central frequency of the bands when these events occurs and the flux?
Central frequencies. So when it goes into the quenching mode in these regions, we do see some fairly bright bursts, but it varies from burst to burst. Sorry, burst storm to burst storm. But in terms of strict correlation, in terms of high SNR bursts in specific bands, we don't strictly see any correlation if we take the whole 16 month of data. So yeah.
Thank you.
Yeah.
Nice talk.
Thank you.
I think we have to move on. Please take the speaker. Next speaker is Meghna, and she'll talk about, AstroSat searches.
Yeah, I hope I'm audible. So hi everyone, I'm Meghna and I graduated from IIT Bombay. And today I'll be presenting the results from AstroSat-CZTI searches for hard X-ray prompt emissions from FRBs. So first, a brief introduction about AstroSat. So AstroSat is an Indian multi-messenger space mission launched in 2015 in the low Earth orbit. And using the CZTI module on board AstroSat, we have already detected over 700 GRBs in the past 9.5 years. So for the FRB dataset that we used for our searches, we had around 968 FRBs and these are the publicly reported FRBs. And after correcting for the arrival time delays, we ran our search pipeline for detecting the X-ray prompt counterparts. And what we found was that for around 60% of the FRB sources, we had coincident CZTI data. And unfortunately, for any of these, we did not detect any X-ray candidates. But we did the next best thing and found the X-ray flux and fluence limits, with the most constraining ones coming from the 10 millisecond search bin. And in the plot for the X-ray to radio fluence ratios, you can see that the results are consistent with the limits that we got from our previous study, as well as the ones obtained from similar missions such as Swift-BAT and slightly deeper than the limits from CONUS wind search. And we can also observe that we have a lot of samples at a high value of eta. And this is consistent with the fact that radio telescopes are detecting fainter and fainter FRBs, but the sensitivity of X emissions has not improved by a similar margin. We also calculated the upper limit the energetics of the upper limits. And here we have two plots. One is for the isotropic equivalent luminosity and the isotropic bolometric emission energies. And we can observe from these limits that the equivalent luminosities of both short and long GRBs are actually higher than some of the limits for many of the events. And this points to the fact that short GRBs and long GRBs might not be, are unlikely progenitors, excepting the low luminosity GRBs, like the short GRB that was observed from GW170817. And this also points for the need for searching for low luminosity GRBs, as was already discussed in some of the previous talks. So over here, I'll take the chance to promote Daksha, which is a proposed project. And this will have an order of magnitude higher sensitivity than the current project and an all sky coverage. So using Daksha, and we can, so not just Daksha, but we calculate the joint detections that we can observe in the next 5 years for X-rays and FRBs. And we observe that large field of view missions such as AstroSat, Fermi, and Daksha will complement large field of view radio telescopes like BURST. And I'll end over here. And if you're interested, please feel free to read our paper. Thank you.
Just have time for one question if anyone has any. Okay, do the next. Thank the speaker again.
Thank you.
Our next speaker is Maura. You'll talk about, I guess, R3.
Yes.
Yeah.
Good morning, everyone. So I'm going to talk to you about how we've looked for a counterpart, multi-wavelength counterpart of R3 in all these years. Just in case you get bored during these 3 minutes, here are my conclusions. We haven't found a counterpart over 5 years of, let's say, sparse monitoring, and we've learned that this detection is actually very challenging. But let me go back to the basics of this. So in 2020, the periodicity of R3 was announced. We started following it up with a Sardinia radio telescope. And during our very first observations, we found these 3 bursts at 300 megahertz. And we had a multi-wavelength campaign lined up for these observations. Unfortunately, let's say this burst happened during the day, so we didn't have optical coverage, but we did get to have a simultaneous X-ray and soft gamma ray coverage with XMM Newton and Agile minicalorimeter. Our upper limits on the energy of this burst were at the level of, let's say, 10 to the 46 Hertz, which were interesting because at the time, the only comparison we had was the brightest flash optical giant, X-ray giant flare of a magnetar in our own galaxy, SGR 1806. The thing is that since then, we've moved away from the idea that this can be the counterpart of fast radio bursts, both thanks to limits like ours, the non-detection in radio that was mentioned yesterday, and in particular, the fact that then SGR 1935 did a very different X-ray burst simultaneous with the radio burst, which was a very regular X-ray burst of energy of the order of 10 to the 39 Hertz. This, though, gave us a very much needed baseline, which is the ratio of X-ray to radio energy is in the range of 10 to the 5, 10 to the 6. And this is what we're looking for. So we published the results of our following part of the campaign in a paper by Matteo Trudo. As you see here, we added to the number of our telescopes, and this time we also had optical simultaneous observations. I want to stress that we're using 2 of the best instruments in the field. Unfortunately, they're not mounted at the biggest telescopes, but these 2 optical photometers, Aqui Plus and CFAP2, they can reach time tagging, photon time tagging of order nanosecond or sub-nanosecond. So in order to look for prompt counterparts, they are the perfect instruments. We didn't find anything in optical, but we got to very deep upper limits here. The ratio of energies between optical and radio is of order of 10 to the second. And unfortunately, this is not constraining because we don't have the equivalent of the galactic magnetar in optical. We just know that even in this case, magnetar hyperflares are to be excluded. Now, we haven't found a counterpart, as I said. In the X-rays with the new campaign, we got similar results to what we had with XMM. Basically, we're still 1 order of magnitude above what we need. And so we decided to calculate what it will take to find an X-ray counterparts with current instruments for R3. And basically, this got to a number that is roughly order of 100 hours simultaneously on the source, or equivalently a kilojansky burst. Not so encouraging, especially at the rate that X-ray telescopes are dying on us during this campaign. On the other hand, with the optical, we have a different issue. So we're not seeing optical bursts simultaneously to the radio bursts at a very deep limit. The thing is, we're seeing fast optical bursts at other times. But in order to pinpoint those to the FRB, we'd need at least 2 optical telescopes to be pointing at the FRB at the same time. And this picture shows, well, whoever had worked at the telescope here knows, it happens that 1 telescope doesn't work. If you're combining more than 1, it happens that not all of them will be working together. But to end up on a more positive note, we have for this campaign some very good instruments in Italy. One is the Northern Cross that we've been refurbishing for our FRB studies, and this gives us a lot of time and sky coverage. It's our own telescope, let's say. And we're ramping up with 2 32-meter dishes that we have in Italy. We've been collaborating and learning from Hyperflash. Because what we need here, I hope I've convinced you, it's not high sensitivity. We're looking for the brightest burst because we need to get at least close to those ratios with X-ray in optical. Thank you very much.
Hi, Lauren Rose from McGill. I have a question about the optical observations. You said with the photon tagging.
Yes.
Were those observations like simultaneous to radio, or were they like triggered observations?
No, it's a simultaneous. No, we can't trigger. You don't have a fast optical photometers in radio instruments.
Thank you.
Yeah, hi, Maura. It's Molson here from McGill. And so I kind of had a question that is again related to the like fast blue optical transients, like the prompt counterpart that you might expect. So I guess like the big experiments that have large all sky coverage, some of them do difference imaging to look for transients, but I expect the time scale is much larger than what you need. But I guess like that must provide some limit on really bright transients that would still show up in those images. Are those limits competitive at all, or just we don't even need to think about that?
So I'm probably not extremely qualified to talk about those limits. I think those were the ones that who was it described them this morning, the Kilpatrick results, maybe it was Alex. So I think it's the same as for FRBs. If you're integrating over 1 second, then you might get to those, but it's very hard if we expect them to be on the order of milliseconds.
Okay, thanks.
Hi, this is Adam Dong from NRAO. I was wondering, you're looking at repeaters where, especially R3, which has 16-day period, so you know when it's going to come, you have radio. Is there any chances of like stacking many optical images on top of one another to find optical counterpart? And have you done it?
Yes, so we've it's very difficult because the optical background is also not very well constrained as we would expect. So we get events that we're still not sure what they are. That's also why we need simultaneous observations. I'm not entirely sure that we've done stacking. No. But I would say it's like in the X-rays, you're stuck in very rare photons. So the background is really something that you have to take into account. We are doing studies on how to take into account what's happening in our background, which is, as I said, very badly constrained in the ocean.
Thank you.
Okay. I think our next talk is online. Yep. Please thank the speaker.
Okay, Zhang, are you online to share your screen?
Yes, can you see my screen?
Oh, sorry, yes. Thank you. Yeah.
Okay, Xian is going to talk about self-absorption in PRS.
Go
ahead,
thanks.
Xian.
Can you hear me? Sorry?
Yes.
Oh, okay. Hello, everyone. My name is Zhang. I'm glad to be able to give this online talk. So I will be focusing on some introduction and discussion of SSA of radio counterparts associated with the FRBs and its implications to FRB origin, with a special focus on the radio counterpart of FRB 2024-0114A. So we know as of yet, we have confirmed a handful of PRSs associated with the FRBs, and also some other candidates, including FRB 2019-04 70A, shown by Alex on Tuesday, and previous theoretical works by Yuanpei Yang et al. And observations support that PRSs are synchrotron emitting nebula around the FRB sources, for example, magnetar wind nebulae or hypernebulae. In the past decade also, despite a handful of radio spectrum of PRSs have been obtained, we still lack evidence of evolution and SSA in their spectrum. You can see here the plots show the spectrum of the compact PRSs associated with the FRB 2012-11-02A and 2019-05-20B. They both have a rather flat spectrum, but lack of a spectrum break in low frequencies. The precise numbers and their evolution are not clear and are also hardly achievable with even current VLBI facilities. therefore hindering more interpretation of their properties. So FRB 240114A is an active repeater discovered last year. We first discovered the associated radio counterpart last year. Our observations and VLBA observations from Bruni et al. Confirmed the compact nature of the source. In the upper plot, we can see the detection of a spectrum break at about 1.6 gigahertz, 6 gigahertz with VLA observations and low frequency UGMRT measurement given by Basha et al. This is consistent with a SSA break. Combining SSA and equipartition arguments as shown with the orange and green thick lines in the bottom plot in this red circle, we can solve for the size and the B-field strength. The size is 10 times more compact and the B-field strength 10 times higher than other PRSs. This may indicate the source corresponds to earlier phase of FRB evolution and indicates a newborn FRB engine. As for B-field configuration, we are able to investigate the line of sight B-field strength. We have two solutions for DM. One is from the bursts. The other is from the energy density of the radio counterpart itself. We therefore constrain the line of sight component at least 3.4 times less than B equipartition value. For more moderate line of sight values, we can conclude that the line of sight value is much smaller, which points toward a point influx dominated outflow and a newborn FRB engine. Besides the peculiar spectrum we see here, the source also shows evidence of a radio flare. With the new observations taken early this year, we update the E-folding rise and decline timescale to just above 200 days, implying a compact nature of the source of less than about 0.2 parsec. With these timescales, we can compare them with that of some slow radio transients. As shown in the left plot, you can see the source is in the red circle in the space taken by the most luminous supernovae and the dimmest end of radio flares from low luminosity AGN. More interestingly, as shown in the right panel, the source tends to join the engine-powered supernovae. So I think more observations are needed to follow this source up to constrain the temporal and spectrum behavior. So I will stop here and thank you, everyone. I'm happy to take questions.
You have questions?
Hi, it's Bill. Could you go back 2 slides to where you showed this radio spectrum, please?
This one?
Yes. So you said that you think this is the synchrotron self-absorption break, but your low frequency spectral index is pretty shallow. How do you rectify that with it being self-absorption? Like, should it not be steeper, more like 2 or 2.5?
Sorry, 1.6?
No. The spectral index at low frequencies, you say there that it's
the low frequency is
0.7.
Yeah, 0.7 minus 0.7.
But at low,
low band, right? Low band, 0.9.
Yeah. But if it was self-absorption, would it not be steeper, more like 2 or 2.5 rather than 1? Like, how do you rectify that with it being self-absorption?
Because the spectrum is non-thermal and the brightness temperature is high, the source is compact, so we conclude it as a self-absorption rather than like free absorption process.
Okay, I'll message you. Yeah. Okay, don't worry. Thanks.
Okay, thanks, Robin.
Okay. Any more questions? I think we have to go to the discussion now. Okay.